Bismillahirrahmanirrahim. Today we'll be talking about interaction between macroscopic systems. This lecture is a part of lecture series from the course of Statistical Mechanics, having the course code of PHY231. The basic objective of today's lecture is to understand the interaction between various macroscopic systems. We can categorize the different sort of interaction, which include the mechanical interaction, thermal interaction, and general interaction. Basically, we already discussed isolated systems. Isolated systems are systems which are not interacting with the surrounding. That is not exchanging energy particles in, and the energy level of that is fixed. So that is why we have considered a sort of isolated system in equilibrium when we were calculating the probability of any particular systems. So in today's lecture we are basically interested in the system when it is interacting with the surrounding, whether it is exchanging energy, particles, or mass, or maybe both. So definitely when a system is interacting with surrounding, the energy level of that system changes. It might increase or decrease depending on the difference between the energy levels or the interaction between the two systems. If we consider any particular systems that is not isolated, so it can interact with the system in various ways, and the result is that the parameters or the external parameters are changed. So to describe the system macroscopic property, we specify its average energy along with some measurable external parameters that are generally represented by various variables, or maybe here we can describe the names as x1, x2 up till xn. So some example of a system external parameters are volume, applied electric field, applied magnetic field, and etc. So of course the quantum mechanical energy level of this system depends on this external parameter through the equation of motion. So the energy of the system many-body system, the quantum mechanical microstate that is labeled as R is specified by its quantized energy levels. As we know that any particular microstate could be represented by ER, and ER has fixed external parameter, just like we can represent the ER by ER x1, x2 up till xn. So the macroscope of that of the same system can be defined as by specifying the system's average energy. So for an ensemble of similar systems, all in the same macrostate, we can find any one of these systems in a huge number of different microstates. So we already understood that there are many microstates that are possible in a particular macrostates, so that correspond to the same macrostate. So from the previous discussion we already know that these are characterized by the simple equation, that is the sigma E, that is the state available in that system, that is equal to a e ki power f, where f describes the degree of freedom of that particular systems. So now we are coming toward the interaction when it is the exchange of energy. For this purpose we need to consider two macroscopic systems that are represented by A and A dash. This is system A and this is A dash. So both the systems are interacting with each other, and in thermal equilibrium, when the systems is thermal equilibrium, so we can say that there is both the bodies are at the same temperature. So interaction is actually the exchange of energy in this particular case when we are considering the thermal interaction. So we assume that the total system energy that is a bar is equal to, that is a0 is equal to a plus a bar, that is the isolated at equilibrium, and a bar are interacting And in similar system is shown schematically in the figure. We focus the attention. We basically consider the system A which is interacting with A dash. So how many sort of interactions are possible when two systems are interacting with each other? So the one possibility is the thermal interaction. In case of thermal interaction, the external parameters remain fixed. I mean the value of x1, x2 and up till xn is unchanged, and the quantum energy levels are also unchanged. However, the population of these energy levels change. I mean the total energy of that particular system remain constant. However, the population of this particular energy levels, so the occupation probability of these level changes. And we have another type of interaction that is actually called as mechanical interaction. In case of mechanical interaction, the external parameters x1, x2, x3 up till xn do change, and the quantum energy levels, that is ER, x1, x2 up till xn, are shifted. I mean in this case both the quantum levels and the external parameters are changed in case of mechanical interaction, while in thermal interaction it is unchanged. However, the population of this energy level changes. So we are coming toward the detailed study of thermal interaction, and for this purpose we need to consider two macroscopic systems, that is A and A dash, and both the systems are interacting with each other and in thermal equilibrium. Consider this is the case where there is a thermal interaction only and no mechanical interactions. So we are specifically consider the thermal interaction in this case. This is system A and this is system A dash. So what happened? We need to focus on system A, which have some particular energy, no mechanical interactions. That means the external parameter of this system, the x1, x2 and up till xn remain fixed, and no work is done because there is no sort of any mechanical interaction. So xi should be a constant quantity. So the total energy of the system is A0 should be equal to A plus A bar A dash, that is isolated and equilibrium. So there is the energy of system A is conserved. So if we consider both the system as a single system, so the total energy of that system is conserved and the external parameters are also remain fixed, but the systems, I mean the two system A and A dash, which are actually in combined A0 systems, its energy is exchanged with each other. So this is out of thermal interaction. So we need to define the heat, that is actually the mean energy transfer from one system to another as a result of a purely thermal interaction, and more precisely due to its interaction with A dash, the mean energy of A is changed by an amount del E, and del E is equal to Q, that is actually the heat absorbed or emitted by system A. And the magnitude, the Q should be positive or negative depending on the situation. If the temperature of A is greater than A dash, so definitely the heat will leave the system, and this should be negative for this particular case. And if the temperature of A is less than A dash, so what happen? The heat will come from A dash to A, and as a result the magnitude of Q should be positive. So similarly for A dash, the mean energy of the system could be written as del E dash should be equal to Q dash, and that is actually the heat absorbed or emitted by A dash. Again in this case it depends upon the energy level of A. If it is less or greater, resultantly the heat will come or go out of the systems. So we have E0, that is equal to E plus E bar, that is a constant quantity, and the total energy of that system is a constant quantity. And if we can calculate the heat that is taken out from one system, that is taken out from one system and the other system has absorbed, so what happen, we can get, or we can conclude from these equations that the heat absorbed by one system should be equal to the heat given by other systems. So the total energy of that system is conserved. So because the system is placed in an isolated configuration, and so the only conclusion from this we get that the heat absorbed by one system should be equal to the heat given out by other systems so the total energy of that system remain conserved. So now we are coming toward the mechanical interaction, and for this mechanical interaction we consider two macroscopic system A and A dash interacting with each other and in thermal equilibrium. Consider the case where there is a mechanical interaction only, no thermal interaction. In this case energy is not exchanged, only the mass is exchanged. So this is sort of only mechanical interactions. So for this to occur, they need to be thermally isolated, insulated from each other, and this is achieved by surrounding the system with an adiabatic envelope. So an ideal partition which separates the two systems A and A dash, in which external parameters are fixed and each of which is in internal equilibrium, such that each subsystems remain in its macroscopic state indefinitely. So obviously this is an idealization. Definitely when there is some sort of mechanical interaction, some thermal interaction will also occur, but this is what we are considering to be the ideal situation, when there is no sort of no thermal interaction, only the mechanical interaction occurs. But this is a type of ideal situation, and it is very hard to do to make arrangement for such type of interaction. So we are considering an ideal mechanical interaction only, where physically this adiabatic envelope is such that there is no energy or heat transfer can occur between the two systems, that is A and A dash. So what we can see, this is a type of idealization, what we already told. The systems are insulated from each other, they are still capable of interacting through that is actually the change in their external parameters. And what happened, the change in the external parameter due to the mechanical interaction. So in this system, the two systems do mechanical work on each other. So we have a simple example where gas is enclosed in a vertical cylinder by piston, and what happened, the pressure we reduce or increase, and as a result work is done. So we have a system that is A, that is the gas plus cylinder, and we have another system that is piston plus vat. So both the systems are interacting with each other, and due to this interaction of these systems, the energy level of this system change, the work is done, and we can calculate the magnitude of work done. So we consider these systems due to mechanical interaction with system A dash when its external parameter changes. So does this mean energy change? That is denote this as a del XE, and the macroscopic work done on the system is defined as W is equal to del XE. We can calculate the magnitude of this macroscopic work done, and that is equal to W is equal to del XE. So interaction involves change in the system's external parameter, that are actually the gas volume and piston height. So the system A is in mechanical interaction with A dash, and its external parameters changes this mean energy change, that is by del XE. So the macroscopic work done on the system is equal to W is equal to del XE. So the macroscopic work done by the system is defined to be negative of this W. So that is work done should be equal to minus W, and it should be equal to minus del XE, because work is done by the system, and when work is done by the system is always taken as a negative. Now coming toward the general interaction, that is actually the combination of both mechanical and thermal interaction. In this case, both the thermal interaction and mechanical interaction occur simultaneously, as this means that in the meantime the energy is exchanged and the particle or the mass is also exchanged, and the combination of this is called as a general interaction. So we consider two macroscopic systems A and A dash again with each other, and both the systems are interacting in thermal. Both the systems are interacting, and in the case of thermal equilibrium, one in which no mechanical work is done. So the energy exchange between A dash is A and A dash is heat exchange. So we apply the law of conservation of energy for the combined system. The total energy of this combined system is equal to del a 0 average, that should be equal to del E average plus del E dash average. So what happened? Del E average should be equal to Q, that is heat absorbed or emitted by system A, and the same should be del E dash average or Q dash should be equal to the heat emitted or absorbed by system B. So again we are coming to the same conclusion in case of thermal interaction, that the heat emitted by one object or one system should be equal to the heat absorbed by other systems, because we can consider the ideal situation. So if the bodies have different temperatures, so the heat absorbed by one body, the heat released by one body should be equal to the heat absorbed by another body. So coming to the mechanical interactions, one in which we can consider a system that is A and A dash that are thermally insulated from each other and no heat exchange is possible. But in this case heat exchange is also possible. I mean, at the same time mechanical work is also done and heat is also interacting. I mean heat is also exchanged. So they interact by doing mechanical work on each other through changes in their external parameters. So the macroscopic work done here is on, and that is the magnitude of macroscopic work done, W is equal to del XE. The magnitude of W should be equal to W is equal to minus W small w, that is equal to minus del XE. So the conservation of energy again valid for the combined system, and the total work done or the magnitude of W plus W dash should be equal to each other. That is the so the most general case of the is one when the thermal and mechanical interaction are at the same time. This external the external parameters are not fixed. A and A dash are not thermally insulated from each other. So this sort of interaction is actually called as the general interaction. So as a result of this general interaction, the mean energy of A is changed both by change in external parameter and by a transfer of thermal energy. So this mean energy change may be written as a del E is equal to W plus Q, or del E should be equal to minus W plus Q, and that is the change in their mean energy. So should we apply the law of conservation of the first law of thermodynamics on this interaction between different systems, in which the total energy is equal to heat plus mechanical work done. That also describe this as a law of conservation of energy if you look toward this equation, and that law says that total energy provided to the system is equal to the heat change, that is actually the thermal interaction plus mechanical interaction. So we have a good example of general interaction is the first law of thermodynamics, where total energy is changed, and that is changed by the heat change, that is the thermal heat change is thermal interaction, and mechanical energy is the type of mechanical interaction. So this is a general interaction, we are coming toward that. This is a simple example of general interaction where Q is equal to del E plus W. So the first law of thermodynamics also describe the conservation of energy, that the total energy of the system is conserved and the total energy is equal to heat plus mechanical energy. So from it we can get that two interactive systematic equilibrium. The first law says that the total energy is conserved, but it says nothing about the direction of energy transfer between the two systems. So to understand this, in the first law of thermodynamics, the direction of energy is not specified. So if you are looking toward the direction of energy, we need to understand the second law of thermodynamics, and that is something about the second law of thermodynamics what we can get the class. So this is to study the law of fundamental understanding of the relation of the classical thermodynamics. So we need to understand the second law of thermodynamics to further investigate the direction of energy, that in which direction heat will flow and heat will move from that. So this is a simple sort of interaction, that is the heat absorbed and by one system should be equal to the heat released by other system, that is from the first law of thermodynamics. We can also write the same thing in the form of equation, that heat given up by a system should be equal to the heat taken by another systems, and that is actually the first law of thermodynamics, an example of the general attraction in any particular systems. So this is simple case about that things. So I hope we can move forward in the next classes. Here we have some example of external parameter when it is changed, and the example of generalized force. We have external parameter, that is x alpha, that is position coordinate, volume, electrical potential, and electric potential and magnetic field, and similarly electric field. We have generalized forces, that is mean generalized forces might be mean mechanical force, mean pressure, mean electric charge, mean magnetic moment, mean electric dipole moment, and that will lead to the macroscopic work done. The magnitude of macroscopic work done could be calculated by dw is equal to f average dx, and similarly p average dx and q average dx. And for any particular system we have different notation and different variables that are involved in that. So this is something about the interaction between macroscopic systems. Thank you very much.